Example is going to be more advanced. It will feature more difficult functions, and we'll have to actually draw branch cuts in a complex plane. So let's start. So our equation looks like this. Right. So let's write down our P and Q polynomials. So P polynomial, if the polynomial composed of these coefficients which don't contain x. So no polynomial with so it's simply t. So and Q polynomial is t squared plus 1. So the integral of P over Q is t dt over t squared plus 1 is simply 1/2 of the corresponding log function. Now we are ready to write down the exact solution of this differential equation in terms of a contour integral. So z function is e to this integral, so it's e to 1/2 of the corresponding log, which is simply the square root of t squared plus 1. V function is, as you remember, z times, z function, yeah, it's this function divided, by q, of course. So which yields 1 over square root of t squared plus 1. Right, so v function is z function multiplied by q multiplied by e to xt. So it's going to give us e to xt times the square root of t squared plus 1. And here is the exact solution. U of x is equal to the contour integral in t domain of z function times the exponential term, like this. So we are interested in the solution which is bounded at infinity and at the origin. So we'll fix it by the condition that u of 0 is equal to 1 and u of x is bounded at, for example, at x going to plus infinity. So here we go. So this is our v function, which defines the approximate position of our contour. Actually, it fixes eventually the position of our contour combined with our boundary conditions. So let's draw a complex plane. But what you've noticed is that our v function is in fact a multivalued function because it contains this square root. So it has two branch points, t is equal to I and minus I. And now we need to draw, to define it completely, we need to draw a branch cut. So there are different configurations of branch cut. For example, you can draw a branch cut from point minus I to negative infinity to any direction. Or you can actually draw a branch cut connecting these 2 points, minus I and I, and then again the regular branch of this function will be fixed. So in this example, from pedagogical reasons, I will choose the simpler branch cut which just connects these 2 points, I and minus I. Okay, so here it is. The other peculiar thing that you notice, so you always seek for the point in the complex plane where your v function vanishes. So there are at least 2 obvious points where it happens. These are these branch points, I and minus I. V at these points vanishes, right? But there are another ones. For example, if t is chosen such that the real part of xt is negative, then when t tends to infinity, when t becomes large, then this exponential decays. And then if we are lucky to find these regions in where it happens, then in this region the function also vanishes. All right. So in our particular case, for example, we consider the case where x is positive, and that means that t should belong to the left complex semiplane. So the real part of t should be negative. Okay, so how do we choose now the possible contour configurations? Well, one could choose, for example, like I told you before, the contour which connects simply two branch points. So something like this would be our first contour. And the second contour, well, one is tempted to draw something like this, which completes this like to a full circle, but this won't give us the linear independent solution. So instead we should try to draw some kind of completely different contour. So in the spirit of what I told you before, you may draw a contour, say, coming from point I and going in some direction to infinity in the left complex semiplane. Right, so now, and this will be our second contour. So now we have two linear independent solutions of our initial equation. Right, so let's write them down. So they're defined up to some constants, 1 and 2. And the contours are C1 and C2. And solutions are the first one and the second one. So let's first investigate probably the second solution. So U2 of x. So we are interested in the solutions which are bounded at the origin. Let's try to figure out how this solution U2 of x, defined by this contour C2, behaves at small x, or at actually x is equal to 0. So suppose x is equal to 0. Then we should put 0 here, and what we get is some constant a2 times the contour integral, and the contour integral just stretches from I to say, well, we can deform the contour, so it's better to represent it as a horizontal line which tends to minus infinity. So the integral is taken from I to minus infinity dt over square root of t squared plus 1. So what do we notice? At t is equal to I, the integrand has a soft singularity because it contains this square root in the denominator, so it's an integrable singularity. So the answer, so the integral converges at the lower limit. But at the upper limit, you clearly see that at large t, square root of t squared plus 1 behaves like t, and you have the divergent integral dt over t. So what does that mean? That means that, so instead of just trying to figure out how the solution looks like at the origin, it's actually better to consider this solution when x is small but non-zero. Then again, we should get rid of this exponential, change it into 1, but we can do it only when this exponent of this exponential is small. So u of x is equal to the same integral a2 times dt over square root of t squared plus 1 from I to minus infinity. We should actually, so the change of this exponential to 1 is only true for t which is much smaller than 1 over x. So the exponent of this exponential is small. So the upper limit of this integral is of the order of 1 over x. And now we come to the estimate of the behavior of our solution u2 of x at small x. So the integral becomes the integral from, so the lower limit becomes irrelevant because it's a divergent integral. So we just integrate dt over t. And with logarithmic accuracy, we get the result a2 times the logarithm of 1 over x. So now you see why we get the divergent answer, because the function u2 has a logarithmic singularity at the origin. So this contour is no good for us. We are looking for different solution which is finite at x equal to 0. So let's try to study another one, u1 of x.